7. We're going to look at the precise definition of a limit. And so here it is, if we have some type of function on an open interval and we're getting closer and closer to a, what is the y value getting closer and closer to? That's kind of what we understand limit to be. Well, here's a more precise definition. Okay, because maybe what happens is you have your graph and maybe I'm approaching, say, 4, and normally my answer is 7, right? So the limit as x goes to 4 of some function is 7, right? So maybe it looks something like this, if I can draw, right? Maybe there's a hole here and the graph keeps on going, right? So the limit looks like it approached 7, but maybe if you zoom in, so maybe if you zoom in just a little bit more, it actually looks something, maybe like this. So if I zoomed in, say by 10, maybe the graph, so if I zoom in between here, so let's just pretend like we're zooming in right here, okay? So maybe what happens is the graph goes something like this. So it's approaching, but then it goes like that and comes straight back. And then here's the little thing right here. And maybe this is actually, comes right here and goes, or I guess it would come probably, maybe it comes down right there and then takes off, right? But because you're zoomed in, you can see something changing, where if you zoom out, yeah, it looks like a straight line, but if you zoomed in, maybe it's doing something funky in here, like jumping up and down or something like that. Okay, but because you're zoomed so far out that you can't tell, you just see a straight line, because maybe this is like 4.000000001. Something's doing something different right there, right? You're really, 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 really close to 4, but not quite at 4. Maybe it's doing something funky here, all right? So that's why we need more of a precise definition that says, okay, as long as I can get, and this is basically what it says, as long as I can get, here's my function, right? There's a hole there. As long as I can find some number that is close to my x, that's what this means. Some number close to my x, and it has to be greater than 0. Some number really close to my x. So say it's close, like if I have the number 4, this is 3, and this is 5. Then I can find a number really, really close to my limit, which is called L. That's what this says. A number really, really close to your limit. So if you give me any distance between the x that you have, I can find you a y value that will be close to your limit. So I can find any number distance you give me here. So if I give you 1, I can find the distance in between L, which would be 2. Okay, for this f of x. This f of x is y equals 2x minus 1. Okay, but any equation. So if I give you a distance of 0.5, can you find the distance between this L? Okay, and then you get smaller and smaller and smaller. So that's why this becomes delta and this becomes epsilon. So they're arbitrary numbers, meaning you can put any number. So you can go as small as you want to, 0.000001, and I can find you a number that's going to be in between this L, right? Somewhere close to this L. So I can always find a number. So then that means that something's not doing something funky right in here where you get this number up here, right? You still get in between this. I'm still going to land in between. So that's the more precise definitional limit, and this is kind of how it looks like, how you write a proof of it. You say let epsilon greater than 0 be given. This is what you always start with, okay? And then you'll find, what you want to do is you want to find a delta. So you're kind of going to go backwards. So to find it, you're going to start with this f of x minus L is less than epsilon, and you're going to find your delta. And then when you write your proof, you'll start with epsilon greater than 0 be given, and then you'll say, okay, choose some kind of delta, and you'll have an answer. And then you'll start with this x minus a is less than delta, okay, and then you plug in your delta, what you put in, and then you'll prove that it looks like this. Okay, so let's go ahead and do an example. So the limit as x goes to 2 of f of x equals 4. And here's my f of x. So it looks something like this. It's an x squared, right? So 0, 0, 1, 1, 2, 2, 3, 4. So normally we'd get 4, but this says we don't. It says we actually get 1. And there's actually a hole here. So our graph, looks something like this, and it keeps on going like that. Okay? And so our limit looks like we're getting closer and closer to 4, right? But maybe something happens in here, right? So as we look at this, we want to go backwards. So it's an if-then statement. So if this is true, delta, then this has to be true. I can find a distance in between my limit, epsilon. And if that's true, then the limit exists and the limit is 4. Okay? Or you can say therefore. Okay? So we're going to go backwards. We're going to start with this f of x minus the limit. So here's our f of x, and if we're looking at plugging in 2, okay, we're going to plug it into this one, okay? Because this one doesn't really do anything other than just give you that point. So first we got to figure out what we got to find. We got to find a delta. In order to find a delta, we're going to start with epsilon. Okay, so I'm going to start with f of x minus our limit is less than delta, or epsilon, sorry. Okay, so I plug in my f of x, which is x squared. I plug in my limit, it's 4. Okay, and then I'm going to go ahead and factor this, because what I want to do here is I want to turn this into our x minus our a, and our a here is 2. So I want to turn it into that. Okay, so I need to factor this. Sometimes I need to add something. Sometimes I need to divide or factor something out in order to make it look like x minus 2. Well, I see that this is a conjugate, so I get x plus 2 times x minus 2. So I have the x minus 2 now, but now I have this x plus 2. So if I go ahead and divide both sides by x plus 2, there I have my x minus 2, which that's what I need right here. It's less than delta, or epsilon, divided by x plus 2. Okay, so now I actually have my epsilon, right? Because epsilon goes right here after the x minus 2 is less than delta. So now I keep probably interchanging delta and epsilon, but this is delta, this is epsilon. Epsilon, think E, it looks like an E. Okay, all right, so now I have my delta, so now I can write my proof. We always start this way, let epsilon greater than 0 be given. Then choose delta equal to, what do we want delta equal to? Epsilon over x plus 2. Okay. Then plug it into your x minus a equation, because when we go forward, when we do the proof, we start with if x minus a, then the f of x minus L was what we had to prove. So 0 is less than x minus a, which is 2, is less than delta. So we start there. So then we plug in our delta. So x minus 2 is less than epsilon over x plus 2. Now we can multiply both sides by x plus 2. Then x plus 2 times x minus 2 is less than epsilon. And then 0 is less than that. Put that in there. Then we can go ahead and multiply those. So x squared minus 4 is less than epsilon. Therefore, we proved it, right? We got to our f of x minus L. Therefore, the limit as x goes to 2 of f of x equals 4. Okay, so that's our perf. You can put QED, or you can put this little box thing. QED is, it's Greek for what has been proven, I think. Okay, here's another one. So again, we need to find a delta greater than 0 such that, you know, our f of x minus L is less than epsilon. Okay, so we start there. We plug in our f of x, which is x minus square root of x minus 1. And then we're subtracting our limit, which is 2. Okay. All right, and now less than epsilon. So now we're going to rewrite this. Whenever we have a square root of something, minus something, or plus something, we're going to multiply by the conjugate on top and on bottom, right? So when I multiply by the conjugate of this, I want to multiply by square root of x minus 1 plus 2 on top and on bottom. Okay, so on top is just first times first, which is just that, and last times last, which is just that, and then bottom it stays the square root of x minus 1 plus 2. Okay, and that is less than epsilon. Okay, now we can simplify this as x minus 5, which you can see that's kind of what we want because that's our x minus a, and x minus a is x minus 5 because that's our a is 5. So it kind of starts to look like that. Oops, that's a 2. Okay, that's a minus 1. Getting a little sloppy here. All right, so then we can go ahead and think about how we can get rid of this bottom, right? Because we don't really want that bottom there. Well, if we think about this number, square root of x minus 1 plus 2 in the denominator, right? We know that adding 2 is going to make the denominator bigger, which will make the overall thing smaller, right? The bigger my denominator, the smaller the actual number is going to be, right? So if we think about this square root of x minus 1 plus 2, that's small, right? And what we want here is an x minus 5. So if I have x minus 5, I know that dividing by this square root of x minus 1 plus 2 is going to make that smaller. So what if we have a 2 on bottom? Okay, because if I have this 2 on bottom, then I know something that's smaller than that is if I just add something to this 2. If I add something to this 2, then it's going to make this smaller, right? So if I add, my numerator stays the same, but if I have 2 on bottom, these would be equal, right? But if I add something to this, even a little bit bigger number, then this is going to be smaller than the x minus 5, right? As long as it's smaller, it's okay. Because when I look at the limit, it's okay to get a number that is smaller. So if I want to be between, say, 2, right? So if, say, this is our number 7, like we had that example, this is 4, and I had 2 is 9, and then 2 below is 5, it's okay. It's okay to get a number smaller, right? Because all I'm doing to do is get in smaller here, right? I'm starting here at these two and trying to find this number in between here. So if I start even smaller, then that's okay, right? Because I'm trying to get in between these two. So it's okay to have this thing smaller, right? So in order to get smaller, I just need to add something to that denominator, right? And it'll make it smaller than what I'm actually using here. So that's where I add this, because this is just a number. It's going to get bigger and bigger and bigger, right? It's just going to grow smaller. It's just not going to grow as fast. So if I add to this 2, x minus 1 is exactly what my denominator is, then all I have to do is have a 2 here, and this number right here will be smaller, which is okay because I'm in between what number I actually need, right? And so that's less than epsilon. This probably makes no sense, but we can do some more examples in class because these are difficult. Okay, so now I just want, again, I want to get x minus 5 by itself. So now it's easier to just multiply both sides by 2. And so I get x minus 5 is less than 2 epsilon. Okay. And so now I know what my delta needs to be, right? Because it's x minus a is less than delta. And so my delta needs to be 2 epsilon. So here's the proof. Let epsilon greater than 0 be given. Choose delta equals 2 epsilon. And now we plug in our a. So 0 is greater than x minus my a, which is 5, is less than delta. Then I can plug in my delta. It's 2 epsilon, and now I can start reworking it, right? Which I just come back over here and say, okay, well, I multiply by 2, so in order to get epsilon by itself, I divide by 2. So divide both sides by 2, so that's x minus 5 over 2. It's less than epsilon, and this is where I put this thing back in. Whatever, because I want this thing back in right here. Okay. Okay, and hopefully now this part is going to make sense. Okay, so a little side work. Since, right, this right here, x minus 5 over 2 is less than epsilon, right? Since x minus 5 over square root of x minus 1 plus 2 is less than x minus 5 over 2, right? That's less than that because this is a bigger denominator. So it's going to be smaller than that. So therefore this, okay, let's see if you can think about this. If this is smaller than epsilon, and this is smaller than this, that means that then x minus 5 over square root of x minus 1 plus 2 would be smaller than epsilon, correct? X minus 5 over 2 is bigger than this, then this is going to be smaller than epsilon because this is smaller than epsilon, if that makes sense. Hopefully that makes sense. Now we can keep on going with our work. Now I can multiply by the conjugate on top and bottom. So then x minus 5 times square root of x minus 1 minus 2. And do that on bottom, right? Conjugate on bottom. X minus 1 minus 2. Right, I'm going to FOIL this so I get x minus 1 minus 4, which is just x minus 5. So I get x minus 5 on bottom, x minus 5 on top. This is less than epsilon. All these would cancel, right? So you get square root of x minus 1 minus 2. It's less than epsilon, which is our f of x minus our L. Therefore, the limit as x goes to 5 of f of x equals, what did it equal? What's our L? 2. Equals 2. And I mean, you can write it like that, or you can write it like this. Our function x minus 1. Done. Or QED. Okay, one more example. Hopefully I can make this between 25 minutes. Sorry for the longness, but sometimes it happens. But you're going to have questions come with questions in class, and we can do some more examples in class. Okay, so I need to find my delta, right? And in order to find my delta, I plug in my f of x, subtract my L. Okay. And again, when you have something like this, you're going to multiply by conjugates, top and bottom. Really, this is all the same except for I have x minus 9 for my a rather than x minus 5, right? So I want to get here. Make this look like this. So we're going to multiply top and bottom by the conjugate. Plus 2. So bottom is just going to be square root of x minus 5 plus 2. Okay. So top is just going to be x minus 5 minus 4, which is our x minus 9, which you want. And on bottom is the square root of x minus 5 plus 2. Now it's the same thing as before, right? I can get a number bigger than this by just keeping the 2 on bottom and getting rid of the square root of x minus 5. So x minus 9 over 2, right? This would be smaller than this. So that's smaller than epsilon. Okay. Then I multiply both sides by 2, multiply both sides by 2. So now I have my delta, sorry. Now I have my delta 2 epsilon. Okay, so now we go back through, let epsilon greater than 0 be given. Always start with that. Then choose your delta, some form of epsilon. And then you can plug in 0. So 0 x minus a is less than delta. Now plug in your delta, which is 2 epsilon. Then you can go ahead and start doing your work backwards, right? So divide by 2. Since x minus 9 over 2, and this would be smaller than that, x minus 9 over square root of x minus 5 plus 2 would be smaller than x minus 9, which is smaller than delta, right? Therefore, x minus 9 over square root of x minus 5 plus 2 would be smaller than delta, right? If this is smaller than this, and this is smaller than this, then this is smaller than this. Hopefully that makes better sense than the last one. All right, then we can multiply by the conjugate. All right, top and bottom, we get x minus 9 is over it's times by square root of x minus 5 plus 2. And the bottom multiplying by the conjugate, we would just get x minus 9. These would cancel. We get square root of x minus 5 plus 2. Sorry, the conjugate would be minus 2. Minus 2. Minus 2. Okay, this is all less than epsilon, which is less than epsilon, which proves our f of x minus L is less than epsilon. Therefore, whatever, the limit as x is it goes to 9 of f of x, which is x minus 5, equals 2. Done. All right, sorry for the long video. Hopefully you could go through the examples. Hopefully this last example helped better than the one before that, but sorry. But we can go over more in class, but that's it.